Alright, so just like in proteins, it's not enough to just discuss the foundation or to discuss the building block. It's also important for us to see how these building blocks are actually linked together. So in proteins, we know now that they are joined together. These amino acids are joined together by peptide bonds. So what joins the the nucleotides together? Well, here we're going to discuss it now. So given I have two nucleotides here, okay, the important part here is the sugar. Alright, it's the focal point of the bond that would join these nucleotides together. Alright, so what would happen is the phosphate group's going to participate with the sugar of the other one. Okay, so we know that this one has a phosphate group attached to the 5' carbon. Alright, but remember that this phosphate group is still negatively charged. Alright, and just to complete the drawing here, whether the sugar is ribose or deoxyribose, the OH at 3' will never be gone. Alright, the only OH that will be removed in case of deoxyribose is the one at 2. Okay, so whether it's ribose or deoxyribose, the OH at 3 would remain. So it's actually the hydroxyl of 3 and the phosphate group of another nucleotide that would bond. So if we would demonstrate that here, just like in the formation of an N-beta glycosidic bond, just like in the formation of a 3-phosphoester bond, we would remove another OH here, and this time we would link the phosphate group of this one to the 3' carbon of the first. Alright, to the 3' carbon of the first. And that would also remove the double bond here. And again, we know that this one is called a 3'. The bond here of phosphate in 5' is 5' phosphoester. But to the 5' phosphoester bond, we added another phosphoester bond, which is located at 3'. So now, we call the bond that joins the two nucleotides a 3' because of this, and then a 5' because of the original bond, phospho. Now we have two phosphoester bonds, so we call it a phosphodiester bond. So this is kind of the equivalent of the peptide bond when it comes to nucleic acids, because it is what joins the two nucleotides together. Alright, and this shows the importance of the phosphate. We cannot just have a nucleoside here, because if we have a nucleoside here without a phosphate group, it's impossible for you to have a phosphodiester bond. It's impossible for you to join these building blocks together. Alright, and this does not just make up the entire structure of nucleic acids that we usually see. Alright, as we recall, nucleic acids like DNA look something like this. Alright, this one is a double helix. If we have tons of this joining together, we just have one single helix, but this one is a double helix. Alright, meaning if we have a lot, this one we make this very long, we just covered 1/2 of the double helix. So where do we get the other half of the helix? Well, it should be formed independently. Alright, it should be formed in another strand like this one. For example, I have here the first helix and I have here the second helix. They should be able to join together to form a double helix, but they should be facing each other in opposite directions. For example, I drew it in this manner, this helix, these nucleotides in this manner. Then I drew the nucleotides on the other helix the other way around. Alright, so they're facing opposite directions. So the property that we're talking about here, or that I'm describing here when we talk about a double strand, is that they are anti-parallel. Alright, they are facing each other in opposite directions. Alright, so another thing is that they cannot just be anti-parallel. There should be an interaction between them, and in particular, the interactions between them should be with their bases. Alright, with their nitrogenous bases. Okay, so meaning that there should be forces of interaction between these bases in order for them to stick together and form what we know as the double helix strands, particularly of DNA. Okay, so the particular forces that we talk about here are van der Waals. Alright, van der Waals, because they are aromatic, whether it's a purine or pyrimidine, these are van der Waals. But also, we have here hydrogen bonds. And where do we get the hydrogen bonds? Alright, so to make it clear, I'm going to find, where is that? I already prepared a drawing for that. Alright, so when they have interactions, now you have one base here, you have one base here, then you call this one a base pair. So that means that a double helix strand, alright, performs base pairing. And in base pairing, there should be rules, alright? There are rules that we talk about here, and the rule is that, first of all, a purine can only interact with a pyrimidine and vice versa. You cannot have a purine and a purine, nor a pyrimidine and a pyrimidine. But in addition to that, you cannot have just a purine interacting with any pyrimidine it wants to. And the particular pattern or trend that should be followed is, if the purine is adenine, it should only interact to thymine or uracil. Alright? And if the purine is guanine, the pyrimidine that it should interact is solely cytosine. Alright? And here you may be asking, when will I know if the adenine would bond to thymine or if the adenine will bond to uracil? Well, later on we will see that thymine would only be present in DNA, and uracil would only be present in RNA. So automatically, if we have a DNA strand here and we know it, adenine is automatically bonded only to thymine, because obviously uracil is not present there. But if we have an RNA, it's the other way around. You don't have thymines in RNA. Automatically, adenine, RNA, would bond to uracil. Alright? So that's the case. And I said that, well, obviously we have here aromatic rings. They would bond by van der Waals, alright, or increased resonance. But where do we get the hydrogen bonds? We have nitrogens here, right? And we know that nitrogens are electronegative atoms. So here we have nitrogens. They take up these partial negative charges and they impart partial positive charges to this one. Also this one, partial negative, partial positive, alright, partial positive. Okay, now in guanine we also have the same thing here, partially positive, partially positive, partially negative, partially negative. Then the same here. Oxygen bonds to carbon. It wins in electronegativity, it will become partially negative. Alright, nitrogen here would be partially negative, partially positive, partially negative. Alright, am I missing something? No. So here in adenine with thymine and uracil, it actually gives us two hydrogen bonds. The first one is this. I forgot to draw this one. Partially negative oxygen, partially positive hydrogen. There you go, a hydrogen bond here. Then another thing here, partially negative hydrogen, partially positive hydrogen. There you have it. So you have two hydrogen bonds with this combination right here. But for this one, let's see. Just to complete the cast. Alright, so we have this one, and we have this one. 1. Partially negative, partially positive, 2. Partially positive, partially negative, 3. So we have 3 hydrogen bonds whenever we get cytosine and guanine base pairing together. So we see that the guanine-cytosine base pair has a stronger interaction. Alright, so if you see a lot of GC, 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 CG base pairs, then it's going to be more compact as compared with adenine and thymine / uracil. Alright.